The closest star to Earth has planets, and at least one of them has a magnetic field strong enough to rival Jupiter's. That is not a typo. A rocky world roughly a third the mass of our planet, orbiting a dim red dwarf just over 4 light-years away, generates a magnetic shield so powerful it triggers flares on its own star. This discovery, confirmed with roughly 99.9% statistical confidence, may fundamentally reshape how we think about the habitability of planets around the most common type of star in the universe. Let us start with what we know about the neighborhood. Proxima Centauri sits about 4.24 light-years from Earth. In cosmic terms, that is next door. It is part of the Alpha Centauri triple star system, though it orbits so far from the central binary pair, Alpha Centauri A and B, that the connection is almost academic. The separation is around 12,000 astronomical units, which is roughly comparable to the distance between our Sun and the inner edge of the Oort cloud. Proxima Centauri is gravitationally bound to Alpha Centauri A and B, but it takes hundreds of thousands of years to complete a single orbit around them. Proxima Centauri itself is a red dwarf. It has about 12% the mass of the Sun and roughly 15% of its radius. If you could place it next to our Sun, it would look like a glowing ember beside a bonfire. Its surface temperature hovers around 3,000 degrees Celsius compared to the Sun's 5,500. It emits most of its energy in the infrared spectrum, which means it is far dimmer in visible light than our star. In fact, despite being the closest star to us, Proxima Centauri is completely invisible to the naked eye. You would need a decent telescope just to spot it. But what makes Proxima Centauri scientifically fascinating is not the star itself. It is what orbits the star. 2 confirmed planets circle Proxima Centauri. The innermost is Proxima d, a small world likely around a quarter to a third the mass of Earth. It completes an orbit every 5 days, putting it extremely close to its star and well inside the habitable zone. Estimated surface temperatures hover around 87 degrees Celsius, though that number comes with significant uncertainty since we have never directly measured it. The second confirmed planet is Proxima b. This is the one that made headlines back in 2016 when it was first announced. Proxima b sits within the habitable zone of its star, meaning that liquid water could theoretically exist on its surface given the right atmospheric conditions. It has a minimum mass of about 1.3 times Earth's mass, making it a so-called super-Earth. Its orbital period is roughly 11.2 days. There is also a third candidate, Proxima c, a potential mini-Neptune on a much wider orbit. But its existence remains heavily disputed, and the evidence is not strong enough to confirm it. For the purposes of this discussion, we will focus on the 2 confirmed worlds, especially Proxima d, because that is where the most remarkable discovery has been made. Before we get to the discovery itself, we need to understand why magnetic fields matter so much for rocky planets, especially ones orbiting red dwarfs. Red dwarf stars are the most common type of star in the Milky Way. Roughly 70 to 75% of all stars in our galaxy are red dwarfs. They are small, cool, and incredibly long-lived, burning through their hydrogen fuel so slowly that they can shine for trillions of years, far longer than the current age of the universe. If life needs time to develop, red dwarfs offer more of it than any other stellar class. But they come with a significant problem. Red dwarfs, particularly younger ones, are violently active. They produce frequent and powerful stellar flares, sudden bursts of electromagnetic radiation that can be orders of magnitude more energetic than the largest solar flares our Sun produces. These flares emit enormous amounts of ultraviolet and X-ray radiation, collectively referred to as XUV radiation. For a planet orbiting close to a red dwarf, which is exactly where the habitable zone sits because the star is so dim, this radiation poses a serious threat. XUV radiation can strip away atmospheric gases over time. It energizes molecules in the upper atmosphere, giving them enough velocity to escape the planet's gravitational pull entirely. Over millions or billions of years, this process can completely erode a planet's atmosphere, leaving behind a barren, airless rock. This is the central concern with habitability around red dwarfs. The habitable zone is close to the star. Close to the star means close to the flares. Close to the flares means atmospheric erosion. And without an atmosphere, there is no liquid water, no insulation, no greenhouse effect, and almost certainly no life as we understand it. But there is a shield that can protect against this, a planetary magnetic field. Earth has one. It is generated by the churning of molten iron in our planet's outer core, a process called the geodynamo. As the liquid iron flows and convects, it generates electric currents, and those currents produce a magnetic field that extends far out into space, forming a protective bubble called the magnetosphere. When charged particles from the solar wind or a solar flare hit Earth's magnetosphere, they are deflected around the planet rather than slamming into the atmosphere directly. Some particles do leak through near the poles, producing the auroras, but the vast majority are redirected harmlessly into space. Without Earth's magnetic field, our atmosphere would be far more vulnerable. Mars is a cautionary example. Mars once had a global magnetic field, generated by a liquid iron core similar to Earth's, but Mars is smaller and it cooled faster. Its core solidified, the geodynamo shut down, and the magnetic field collapsed. After that, the solar wind slowly stripped away most of Mars's atmosphere over hundreds of millions of years. Today, Mars has an atmospheric pressure less than 1% of Earth's, and virtually no protection from radiation at its surface. Venus provides an interesting counterpoint. Venus has no global magnetic field at all, yet it possesses the densest atmosphere in the solar system, with surface pressures 90 times those on Earth. This demonstrates that a magnetic field is not strictly required for an atmosphere to exist. But Venus is also much closer to the Sun than Mars, receives far more solar energy, and may have had its atmosphere replenished by extreme volcanic activity. The conditions are very different from what a small rocky planet around a flare-prone red dwarf would face. So the question becomes, do rocky planets around red dwarfs have magnetic fields? And if they do, are those fields strong enough to actually protect an atmosphere from being stripped away? This has been one of the most important open questions in exoplanet science for years, and until recently, we had very little data to work with. Detecting magnetic fields on exoplanets is extraordinarily difficult. We cannot send magnetometers to these worlds. We cannot directly measure their magnetic fields the way we measure fields on planets in our own solar system. Instead, scientists have to look for indirect evidence. One method involves observing star-planet interactions. If a planet has a strong enough magnetic field and it orbits close enough to its star, the planet's magnetosphere can interact with the star's magnetic field. This interaction can trigger or modulate stellar flares and alter the star's emission patterns in detectable ways. This is exactly what a team of researchers found when they analyzed 3 years of observational data on Proxima Centauri. They measured the flaring activity of Proxima Centauri over this period and found something striking. The star was releasing flares roughly 25% of the time. That alone tells you how active this star is. 1 out of every 4 observations caught the star mid-flare, but the critical finding was not the frequency of flares. It was their timing. The flares were strongly correlated with the orbital period of Proxima d. Every time Proxima d completed an orbit, there was a statistically significant spike in flaring activity. And this was not a marginal signal. The researchers calculated that the probability of this correlation being a coincidence was just 0.14%. In other words, there is a 99.86% chance that Proxima d is genuinely causing flares on its star. Think about that for a moment. A planet roughly a quarter to a third the mass of Earth, smaller than Mars in mass, is magnetically powerful enough to trigger eruptions on its host star. This is not something most planetary scientists would have predicted. The mechanism works like this. Stellar flares are ultimately caused by the star's own magnetic field. Magnetic field lines in the star's corona can become twisted and tangled, and when they snap and reconnect, they release enormous amounts of energy as flares. Now, if a planet with its own strong magnetic field orbits close to the star, the planet's magnetic field interacts with the star's magnetic field. This interaction can stress the stellar field lines, making them more likely to snap and reconnect. The planet essentially acts as a trigger, destabilizing the star's magnetic field at regular intervals corresponding to the planet's orbital period. For this to work, the planet must possess a magnetic field strong enough to meaningfully interact with the star's field across the intervening space. And that is the key conclusion. Proxima d has a magnetic field, and it is not a weak one. Now, determining the exact strength of Proxima d's magnetic field is complicated. There are several unknowns that limit precision. We do not know the exact strength of Proxima Centauri's own magnetic field, which affects how strongly the planet needs to interact to trigger flares. Estimates place the stellar field somewhere between 200 and 2000 Gauss. We also do not know the exact size of Proxima d. We know its minimum mass is about 26% of Earth's mass. But because it does not transit its star from our line of sight, we cannot measure its radius directly. Its true mass could be higher depending on the inclination of its orbit, which we also do not know. What the researchers could do was calculate a range of possible magnetic field strengths for Proxima d, given different assumptions about these unknown parameters. They used the likely range of stellar magnetic field strengths and assumed Proxima d's radius falls somewhere between that of Mars and Earth. Every single combination they tested produced the same fundamental result. Proxima d's magnetic field is stronger than Earth's, not marginally stronger, significantly stronger. The median estimate, assuming a stellar field of around 600 Gauss and a planetary radius similar to Mars, comes out to about 16.4 Gauss. For context, Earth's magnetic field at the surface averages about 0.6 Gauss. Jupiter's magnetic field, the strongest of any planet in our solar system, reaches up to about 50 Gauss near its poles. 16.4 Gauss would make Proxima d's magnetic field roughly 27 times stronger than Earth's, and within the same order of magnitude as Jupiter's. And that is the median estimate. The full range of possible values stretches from about 3 Gauss at the absolute minimum all the way up to 280 Gauss at the extreme high end. Even at the lowest possible estimate, Proxima d's field would be about 5 times stronger than Earth's. At the highest estimates, it would dwarf anything in our solar system. The researchers are careful to note that their estimates are accurate only to an order of magnitude level. The true value of 16.4 Gauss could be off by a factor of 10 in either direction, but the core finding is robust. This planet has a magnetic field, and it is substantially stronger than our own. This raises an immediate and fascinating question. How does a planet this small generate a magnetic field this powerful? To answer that, we need to understand how planetary magnetic fields are generated in the first place. The primary mechanism is a process called dynamo action. It requires 3 ingredients. First, a layer of electrically conducting fluid inside the planet, typically molten iron in the core. Second, convection, meaning the fluid must be actively churning, driven by heat escaping from the core. Third, rotation. The planet must be spinning, which organizes the convective motions through the Coriolis effect and allows them to generate coherent magnetic fields. On Earth, all 3 conditions are met. We have a liquid outer core of iron and nickel, vigorous convection driven by the slow cooling and solidification of the inner core, and a rotation period of 24 hours. The result is a stable geodynamo that has been operating for billions of years. Mars likely had a similar dynamo early in its history, but as the planet cooled and the core solidified, the dynamo shut down. Mercury has a weak but detectable magnetic field, probably because its large iron core still has a thin layer of liquid. But it is so small and the convection so weak that the field is only about 1% as strong as Earth's. For Proxima d, the situation is intriguing. The planet is small, probably between Mars and Earth in size. One might expect such a small world to have a relatively weak magnetic field or none at all, like Mars. But there are factors that could amplify the dynamo well beyond what we see in our solar system. First, tidal heating. Proxima d orbits extremely close to its star, completing a full orbit every 5 days. At this distance, tidal forces from the star are enormous. These forces flex and squeeze the planet's interior, generating heat through friction. This tidal heating could keep the core molten and vigorously convecting far longer than the planet's internal heat alone would sustain. It is similar to what happens with Jupiter's moon Io, the most volcanically active body in our solar system, where tidal heating from Jupiter drives extreme geological activity. Second, there is the question of core composition and size. If Proxima d has a proportionally larger iron core than Earth, perhaps similar to Mercury, which has a core taking up about 85% of its radius compared to about 55% for Earth, then there would be more conducting fluid available for the dynamo. A larger core means a stronger potential magnetic field. Third, despite being tidally locked, which slows the planet's rotation relative to freely spinning worlds, the rotation rate is not zero. Proxima d likely rotates once every 5 days, synchronized with its orbital period. While this is slower than Earth's rotation, it may still be sufficient to organize convective flows into a functional dynamo. A 2012 paper on magnetic field generation in rocky exoplanets found that hot rocky planets with orbital periods of a few days could plausibly generate magnetic fields in the range of 10 to 20 Gauss, consistent with the estimates for Proxima d. There may also be contributions from interactions between multiple planets in the system. Gravitational perturbations from Proxima b could introduce eccentricity into Proxima d's orbit, enhancing tidal heating and thus strengthening the dynamo. This kind of gravitational interplay is well documented in our own solar system. Jupiter's moons Io, Europa, and Ganymede are locked in an orbital resonance that maintains their orbital eccentricities and drives tidal heating in all 3 bodies. Speaking of Ganymede, it is worth noting that this moon of Jupiter is the only moon in our solar system known to possess its own intrinsic magnetic field. Ganymede is about the same size as Mercury, but has a magnetic field, likely sustained in part by tidal interactions with Jupiter. If tidal forces can maintain a dynamo in a moon, they can certainly do so in a planet orbiting even closer to a much more massive body. The discovery of Proxima d's magnetic field is not the first detection of a magnetic field around a rocky exoplanet. That distinction belongs to YZ Ceti b, a roughly Venus-sized planet orbiting a red dwarf about 12 light-years from Earth. YZ Ceti b orbits its star in just 2 days, even closer than Proxima d orbits Proxima Centauri. And like Proxima d, it shows evidence of star-planet magnetic interaction, with estimated field strengths between 8 and 14 Gauss. The similarities between Proxima d and YZ Ceti b are striking. Both are rocky planets. Both orbit very close to red dwarf stars. Both have magnetic fields estimated to be over 10 times stronger than Earth's, and both were detected using the same indirect method of observing star-planet magnetic interactions. 2 data points do not make a pattern, but they are suggestive. If rocky planets in tight orbits around red dwarfs commonly develop strong magnetic fields, driven by tidal heating and perhaps enhanced by large iron cores, then the prospects for atmospheric retention on these worlds improve dramatically. And since red dwarfs make up the overwhelming majority of stars in the galaxy, the implications for habitability across the Milky Way could be profound. Let us now consider what Proxima D's environment might actually look like given this new information. Before this discovery, the default assumption for many planetary scientists was that Proxima D is probably an airless rock. It is small, it orbits a flare-active red dwarf, and it sits well inside the habitable zone, where temperatures are too high for liquid water at the surface under most atmospheric scenarios. The expectation was that Proxima Centauri's intense flaring activity would have stripped any atmosphere long ago. But a magnetic field 16 Gauss strong changes the calculation entirely. A magnetosphere of that strength would extend much further into space than Earth's magnetosphere does, creating a vastly larger protective bubble. The planet's upper atmosphere would be largely shielded from the stripping effects of stellar wind and XUV radiation. Over billions of years, this could allow a significant atmosphere to accumulate and persist. What kind of atmosphere might Proxima D have? That depends on many factors we do not yet know, including the planet's volatile content, its volcanic activity, and the specific composition of any outgassed materials. But we can consider some possibilities. One scenario is a thick, Venus-like atmosphere. If Proxima D has active volcanism, which the strong magnetic field and implied tidal heating would support, then volcanic outgassing could produce a dense carbon dioxide atmosphere. Combined with the planet's proximity to its star, this could create a runaway greenhouse effect similar to Venus. Surface temperatures could reach several hundred degrees Celsius, with crushing atmospheric pressures. Another possibility is a thinner, more Mars-like atmosphere, perhaps with some carbon dioxide and nitrogen, but not enough to create extreme pressures. In this case, the surface might be warm but not uninhabitably hot, particularly at the poles. If Proxima D is tidally locked, which is extremely likely given its proximity to its star, then one hemisphere permanently faces the star while the other is in perpetual darkness. The temperature difference between the day and night sides could be extreme, but with an atmosphere, heat would be redistributed to some degree by winds. The most temperate regions might be along the terminator, the boundary between the permanent day and night sides, or at the poles, where the stellar radiation arrives at a low angle. We could imagine a world with a scorching equatorial region on the day side, a frozen dark hemisphere on the night side, and a habitable ring around the edges where conditions are moderate enough for liquid water. This is speculative, but it is not wild speculation. Climate models for tidally locked planets have shown that this kind of temperature distribution is physically plausible, especially with a substantial atmosphere. There is also the intriguing possibility that a strong magnetic field could enable Proxima D to retain a water vapor atmosphere or even surface water in specific locations. Water vapor is a potent greenhouse gas. If the planet has any surface water, the evaporation and greenhouse warming could create a feedback loop that maintains liquid water in certain regions, even on a planet this close to its star. All of this is contingent on the planet actually having an atmosphere, which we still do not know. But the magnetic field discovery dramatically increases the probability that it does. Now let us turn to Proxima b, the planet in the habitable zone. The evidence for a magnetic field around Proxima b is less definitive than for Proxima d, but it is suggestive. The researchers found no direct correlation between Proxima b's orbital period and the timing of stellar flares. This is not surprising. Proxima b orbits further from the star than Proxima d, so its magnetic interaction with the star would be weaker and harder to detect. However, they did find evidence that the star's emission lines, the specific wavelengths of light emitted by the star's chromosphere, show variations that could be linked to Proxima b's orbit. If the planet has a magnetic field, it would perturb the star's chromospheric activity in ways that alter these emission lines. The signal is there, but it is not strong enough to claim a definitive detection. There is also an alternative explanation. The observed variations could be caused by interactions between Proxima d and a third, currently undetected rocky planet in the system. If such a planet exists, it would need to be very small, smaller than Mars, to have escaped detection so far. Its orbital period would be around 9 days if it orbits in the same direction as the star's rotation, placing it between Proxima d and b, or about 3.5 days if it orbits retrograde, putting it closer to the star than Proxima d. This hypothetical Proxima e is not a strong candidate at this point. It is one possible interpretation of the data, and there is no independent evidence for its existence. But the fact that the data could accommodate an additional small rocky planet in the system is noteworthy. For Proxima b specifically, the implications of a potential magnetic field are enormous. This is a planet already sitting in the habitable zone. If it also has a magnetic shield protecting its atmosphere from stellar radiation, then the conditions for habitability become far more favorable. Without a magnetic field, Proxima b's atmosphere would be under constant assault from Proxima Centauri's flares. Even if the planet started with a thick atmosphere, it could lose significant mass over billions of years. With a magnetic field comparable to Proxima d's, however, the atmosphere could persist essentially indefinitely. The habitable zone designation for Proxima b was always somewhat theoretical. Yes, the planet receives the right amount of stellar radiation for liquid water to exist on its surface, but without knowing whether it has an atmosphere or what kind of atmosphere it has, the designation was just a geometric calculation. The potential presence of a magnetic field adds a crucial piece to the habitability puzzle. It makes a real atmosphere far more plausible. To understand just how significant these findings are, it helps to zoom out and consider the broader context of our search for habitable worlds. For decades, the search for habitable exoplanets was focused primarily on sun-like stars. The logic was straightforward. We know life exists around a sun-like star, namely our own. So the safest bet for finding life elsewhere was to look for similar conditions. Planets in the habitable zones of G-type main sequence stars, roughly the same size, temperature, and luminosity as the Sun, were considered the prime targets. But there is a problem with this approach. Sun-like stars make up only about 7 to 10% of all stars in the Milky Way. Red dwarfs, by contrast, account for roughly 70 to 75%. If we restrict our search to sun-like stars, we are ignoring the vast majority of the galaxy. Moreover, red dwarfs have some significant advantages as hosts for habitable planets. Their extreme longevity means planets have far more time for life to develop. Our Sun has a main sequence lifetime of about 10 billion years, of which roughly 4.6 billion have already elapsed. A red dwarf like Proxima Centauri will burn for trillions of years. If life needs billions of years to evolve intelligence, as it did on Earth, then red dwarfs provide ample time and then some. Red dwarfs are also extremely stable in terms of their luminosity over long timescales. While they have active flare periods, particularly when young, their overall energy output changes very little over billions of years. A planet in the habitable zone of a red dwarf would experience relatively constant conditions for an almost incomprehensible duration. The major concern has always been the flare activity and the question of atmospheric retention. If red dwarf planets cannot hold onto their atmospheres, none of the other advantages matter. A planet without an atmosphere is a dead world regardless of how long its star shines. This is why the magnetic field discoveries around Proxima d and YZ Ceti b are so potentially transformative. If rocky planets around red dwarfs commonly develop strong magnetic fields, then the atmospheric erosion problem may be far less severe than feared. And if these planets can retain atmospheres, then the habitable real estate in the Milky Way just expanded enormously. Consider the numbers. There are estimated to be between 200 billion and 400 billion stars in the Milky Way. If 70% are red dwarfs, that gives us between 140 billion and 280 billion red dwarfs. Studies based on Kepler Space Telescope data suggest that roughly 20 to 40% of red dwarfs have at least one rocky planet in or near their habitable zone. Running the math conservatively, that suggests there could be between 28 billion and over 100 billion rocky planets in the habitable zones of red dwarfs in our galaxy alone. If even a fraction of those have magnetic fields strong enough to retain atmospheres, the number of potentially habitable worlds in the Milky Way is staggering. And this is just our galaxy. The observable universe contains at least 200 billion galaxies, each with their own populations of red dwarfs and rocky planets. The numbers become almost meaningless in their enormity. Of course, habitability requires far more than just being in the right temperature zone with a magnetic field and an atmosphere. The planet needs the right chemistry, the right geological activity, the right water content, and probably a dose of good luck. But the point is that the pool of candidates just got much larger. Let us dig deeper into the science of how star-planet magnetic interactions actually work, because the detection method itself is a remarkable piece of scientific ingenuity. Stars like Proxima Centauri have their own magnetic fields, generated by a stellar dynamo similar in principle to a planetary dynamo, but operating on a vastly larger scale. The convective zone of a red dwarf, the region where energy is transported by the physical movement of plasma rather than by radiation, extends all the way from the core to the surface. This makes red dwarfs fully convective, unlike the Sun, which has a radiative core and a convective outer layer. Full convection means the entire star is churning, and this vigorous motion generates strong magnetic fields. Red dwarf magnetic fields can be hundreds to thousands of Gauss, compared to the Sun's average surface field of about 1 to 2 Gauss. This is part of why red dwarfs are so flare-active. More magnetic energy stored in the corona means more energy available for release in flares. When a planet with its own magnetic field orbits through the star's magnetosphere, the two fields interact. The planet's field carves out a cavity in the stellar magnetic field, similar to how Earth's magnetosphere creates a bubble in the solar wind. But at the close distances involved for planets like Proxima d, the interaction is much more intense. The planet's field can compress and distort the stellar field lines as it passes through them. This compression can trigger magnetic reconnection events in the stellar corona, essentially poking the star's magnetic field and causing it to release energy as flares. The effect is periodic because the planet's orbit is periodic. Every time the planet reaches certain positions in its orbit where the magnetic interaction is strongest, flares are triggered. This is directly analogous to how Io interacts with Jupiter's magnetic field. Io orbits deep within Jupiter's magnetosphere, and its volcanic emissions and the interaction of its own weak magnetic environment with Jupiter's enormous field create a tube of electric current called the Io flux tube. This flux tube deposits energy into Jupiter's atmosphere, creating bright auroral spots that can be observed from Earth. The Proxima d situation is like a dramatically scaled-up version of the Io-Jupiter interaction, but with a planet that has its own strong magnetic field rather than relying on volcanic emissions and induced currents. Detecting this interaction requires precise, long-term monitoring of the star's activity. The researchers used 3 years of data, recording flare events, and comparing their timing to the known orbital periods of Proxima d and Proxima. The statistical analysis showed that flare timing was strongly correlated with Proxima d's orbital phase. The 0.14% chance of coincidence translates to a roughly 3.2 sigma detection in statistical terms, which is strong evidence, though not quite at the 5 sigma threshold typically required for a formal discovery claim in physics. Nevertheless, combined with the physical plausibility of the mechanism and the precedent set by YZ SETI B, The case for Proxima D's magnetic field is compelling. Let us now explore what we know about the internal structures of small rocky planets and how that relates to magnetic field generation. The terrestrial planets in our solar system, Mercury, Venus, Earth, and Mars, share a basic structure. They have a metallic core, primarily iron with some nickel and lighter elements, surrounded by a silicate mantle and a thin crust. The differences in their magnetic fields come down to the specific conditions in their cores. Earth's core is divided into two regions. The solid inner core, about 1,200 kilometers in radius, is composed primarily of iron and nickel compressed to incredible densities by the weight of the overlying material. Surrounding this is the liquid outer core, a layer about 2,200 kilometers thick, made of molten iron alloy. It is the convection in this liquid outer core that drives the geodynamo. The inner core is actually growing over time. As the Earth slowly cools, the outermost layer of the liquid core freezes onto the inner core. This process releases latent heat and light elements, both of which drive convection in the remaining liquid. It is a self-sustaining process that has kept Earth's magnetic field running for at least 3.5 billion years, and it will likely continue for billions more. Mars had a similar setup early in its history, but being smaller, it cooled faster. Its core likely solidified completely, or nearly so, shutting down the dynamo. Some recent evidence from the InSight mission suggests Mars may still have a partially liquid core, but if so, the convection is too weak to generate a global magnetic field. Mercury is an oddity. It has a disproportionately enormous iron core, taking up about 85% of the planet's radius, yet its magnetic field is extremely weak, about 1% of Earth's. This suggests that while Mercury's core still has a liquid component, the dynamics are very different from Earth's. The thin liquid shell may not convect vigorously enough to produce a strong field. Venus, despite being nearly Earth's twin in size and mass, has no detectable magnetic field at all. The leading hypothesis is that Venus lacks the plate tectonic activity that helps regulate Earth's interior cooling. Without plate tectonics, Venus's mantle may insulate the core so effectively that convection in the liquid outer core is suppressed. Or perhaps Venus's core has not yet begun to solidify, meaning it lacks the latent heat source that drives convection in Earth's core. Either way, no dynamo, no field. These examples show that the relationship between planet size and magnetic field strength is not straightforward. Size helps, because a larger planet retains internal heat longer. But other factors, including composition, rotation rate, heat flow through the mantle, and tidal interactions, can be equally or more important. For Proxima d, several of these factors may converge favorably. Even though it is small, its proximity to its star means tidal heating could maintain a vigorously convecting liquid core. Its rotation, synchronized with its 5-day orbit, provides enough spin to organize convective flows into a dynamo. And if it has a large iron core relative to its size, there is more conducting fluid available to generate the field. The result, apparently, is a magnetic field far stronger than what a planet this size generates in our solar system. It suggests that the conditions near a red dwarf can actually be more conducive to strong magnetic fields than the conditions in the outer regions of a planetary system, where tidal forces are negligible. This has implications that extend well beyond the Proxima Centauri system. If tidal heating from red dwarf stars commonly enhances magnetic dynamos in close-orbiting rocky planets, then magnetic field generation may be the norm rather than the exception for habitable zone planets around red dwarfs. The habitable zones of red dwarfs are close to the star precisely because the star is dim, meaning planets in these zones experience strong tidal forces. The very characteristic that was thought to be a liability, close proximity to an active star, may actually provide the mechanism that protects these planets from the star's activity. This is one of those delightfully ironic outcomes in science where a perceived disadvantage turns out to be an advantage. The close orbits that expose planets to intense stellar radiation may also be what gives them the magnetic shields to survive it. Now let us consider the broader history of how we have studied planetary magnetic fields and why detecting them on exoplanets is such a milestone. Magnetic fields on planets in our solar system were first detected through direct exploration. Earth's magnetic field has been known and used for navigation for thousands of years, though its origin was not understood until the 20th century. The magnetic fields of Jupiter and Saturn were detected through radio emissions in the 1950s and 60s. Jupiter in particular is a powerful radio source, emitting strong signals at frequencies below about 40 megahertz, generated by electrons spiraling along its magnetic field lines. These emissions were first detected in 1955 and were initially puzzling until they were connected to Jupiter's magnetosphere. The magnetic fields of the other planets were measured by spacecraft. Mariner 10 detected Mercury's weak field during flybys in 1974 and 1975. Pioneer 10 and 11, followed by Voyager 1 and 2, mapped the fields of Jupiter and Saturn in detail during the 1970s and 80s. Voyager 2 also provided the first, and so far only close-up measurements of the magnetic fields of Uranus and Neptune during its flybys in 1986 and 1989, respectively. These in situ measurements gave us a detailed understanding of how magnetic fields work in our solar system, but they required physically visiting the planets, which is obviously not an option for exoplanets light years away. Detecting magnetic fields on exoplanets requires completely different approaches. Several methods have been proposed over the years. One approach is to look for radio emissions from exoplanets similar to Jupiter's decametric radiation. If a rocky exoplanet had a strong enough magnetic field, it might produce detectable radio signals. Several searches have been conducted using radio telescopes, but no confirmed detections have been made yet. The signals would be extremely faint at interstellar distances, and distinguishing them from other sources of radio noise is challenging. Another method is to look for the effects of a magnetic field on a planet's atmospheric escape. A planet with a magnetic field would lose atmosphere differently than one without. Specifically, the magnetosphere channels atmospheric escape toward the magnetic poles, creating a different spectral signature during transits. Some researchers have claimed detections using this method, but the results remain controversial. The star-planet interaction method used for Proxima D and YZ Ceti b is currently the most productive approach. By looking for periodic modulations in stellar activity correlated with known planetary orbits, researchers can infer the presence of planetary magnetic fields without needing to detect any signal from the planet itself. The planet's influence is read through the star. This is conceptually similar to the radial velocity method used to detect exoplanets in the first place. Just as a planet's gravity causes tiny wobbles in its star that can be detected through Doppler shifts, a planet's magnetic field can cause tiny perturbations in its star's magnetic activity that can be detected through emission line variations and flare timing. The elegance of this approach is that it works best for exactly the kind of planets we are most interested in: small rocky worlds in close orbits around magnetically active stars. These are the planets most in need of magnetic protection, and they are also the ones best positioned to produce detectable star-planet interactions. Let us now explore what the future holds for studying Proxima D, Proxima b, and similar worlds. The James Webb Space Telescope, currently in operation, is capable of characterizing the atmospheres of some nearby exoplanets through transit spectroscopy. However, neither Proxima D nor Proxima b is known to transit its star from our line of sight, which limits what JWST can tell us about their atmospheres directly. There are other approaches, though. JWST can potentially detect thermal emission from close-in planets like Proxima d during secondary eclipses, when the planet passes behind the star. By comparing the total light of the system with and without the planet's contribution, it may be possible to measure the planet's temperature and get clues about whether it has an atmosphere. Ground-based extremely large telescopes currently under construction, including the European Extremely Large Telescope, the 30-meter telescope, and the Giant Magellan Telescope, will have the resolution and sensitivity to directly image some nearby exoplanets. Proxima b, being in the habitable zone of the nearest star, is one of the prime targets for these instruments. Direct imaging could reveal the presence of an atmosphere and potentially even identify specific atmospheric gases. Radio telescopes also offer promising avenues. The Square Kilometre Array, currently under construction in Australia and South Africa, will be the most sensitive radio telescope ever built. It may be able to detect radio emissions from exoplanetary magnetic fields directly, providing independent confirmation of the star-planet interaction results. Additionally, continued monitoring of Proxima Centauri's flaring activity could strengthen the statistical case for Proxima D's magnetic field and potentially confirm or rule out a magnetic field around Proxima b. Longer observational baselines allow for more precise statistical analysis and can reveal subtle signals that shorter datasets miss. There is also the tantalizing possibility of visiting the Proxima Centauri system directly. The Breakthrough Starshot Initiative, announced in 2016, aims to send tiny light sail spacecraft to Alpha Centauri at up to 20% the speed of light. At that speed, the journey would take about 20 years. The spacecraft would be too small to carry traditional instruments, but they could potentially beam back images and basic data about the Proxima Centauri system. This is still very much a long-term aspiration rather than an active mission, but the fact that it is being seriously studied by mainstream scientists and engineers speaks to the unique allure of the Proxima Centauri system as a target for exploration. Let us take a moment to appreciate just how much our understanding of this system has changed in a remarkably short time. In 2016, we did not know that Proxima Centauri had any planets at all. Then Proxima b was discovered, and it immediately became one of the most famous exoplanets in the world. Here was a potentially habitable world orbiting the nearest star. The excitement was immense, tempered only by the uncertainty about whether the planet could actually retain an atmosphere given Proxima Centauri's flare activity. In 2020, Proxima c was proposed, though its existence remains unconfirmed. In 2022, Proxima d was confirmed, adding a third member to the system and revealing it to be more complex than initially thought. And now we learn that Proxima d has one of the strongest magnetic fields ever detected on a rocky planet, and that Proxima b likely has one as well. Each new discovery has shifted the narrative. From a single potentially habitable world around an inhospitable star, the picture has evolved into a multi-planet system where magnetic protection could make atmospheres not just possible but probable. Science works like this. Knowledge accumulates not in a smooth curve but in sudden jumps, each new finding requiring a reassessment of everything that came before. A year ago, most planetary scientists would have told you that Proxima d is almost certainly an airless rock. Today, that assumption is no longer safe. The discovery also prompts broader questions about how we assess habitability. For years, the standard checklist has been fairly simple. Is the planet rocky? Is it in the habitable zone? Does it have the right mass to retain an atmosphere? These are necessary conditions, but they may not be sufficient. A magnetic field might need to be added to that checklist, at least for planets around active stars. But here is the encouraging part. If the Proxima d and YZ Ceti b results are representative, then strong magnetic fields may be a natural consequence of being a rocky planet in the habitable zone of a red dwarf. The same tidal forces that come from orbiting close to the star may generate the very shield needed to survive there. It is a kind of cosmic self-correction, where the problem contains its own solution. Not every rocky planet around a red dwarf will necessarily have a strong magnetic field. The details depend on the planet's composition, its orbital configuration, the presence of other planets in the system, and many other factors. But the fact that we have already found 2 examples from a very small sample is encouraging. Think of it this way. We have barely begun to look for magnetic fields on exoplanets. The techniques are new, the datasets are limited, and the detection threshold is high. The fact that the first 2 rocky exoplanets, where we have managed to find evidence of magnetic fields, both have fields much stronger than Earth's, suggests that we may be seeing just the tip of the iceberg. There could be billions of magnetically shielded rocky worlds around red dwarfs across the galaxy. We just do not have the tools to detect most of them yet. Let us also address an important nuance that is sometimes lost in discussions of habitability. A magnetic field protects against atmospheric stripping, but it does not protect against everything. In particular, high-energy photons, ultraviolet and X-ray radiation are not deflected by magnetic fields. They travel in straight lines regardless of any magnetosphere in their path. What a magnetic field does protect against is the particle-based component of stellar radiation, the stellar wind, and the energetic particles produced during flares. These charged particles would otherwise impact the upper atmosphere directly, heating it and driving atmospheric escape. The magnetic field redirects these particles around the planet, drastically reducing the rate of atmospheric loss. The photon-based radiation, however, still hits the atmosphere full force. This means that even with a magnetic field, the upper atmosphere of Proxima d is still being irradiated with significant XUV flux. This can drive photochemical reactions, dissociate molecules, and alter the atmospheric composition. But crucially, it does not strip the atmosphere away. The gases get heated and their chemistry gets scrambled, but they remain gravitationally bound to the planet. Over time, a planet with a strong magnetic field will retain a much thicker atmosphere than one without, even if both are exposed to the same stellar radiation. The difference is between a planet that slowly has its air peeled away versus one that keeps its air, but has its chemistry constantly stirred. For habitability, this distinction matters enormously. An atmosphere undergoing active photochemistry is still an atmosphere. It can still insulate the surface, distribute heat, support weather patterns, and potentially harbor life. The specific chemistry may be different from what we see on Earth, but chemistry on other worlds was always going to be different. The important thing is that the atmosphere persists. There is another fascinating aspect to strong planetary magnetic fields that deserves mention. On Earth, the magnetic field interacts with the solar wind to create the Van Allen radiation belts, regions of trapped high-energy particles that encircle the planet. These belts are dangerous for spacecraft and astronauts, but are held far above the surface where they do not affect surface conditions. A planet with a magnetic field 20 or 30 times stronger than Earth's would have proportionally more intense radiation belts. The trapped particle population would be much denser, and the belts would extend to greater distances from the planet. This would make the space environment near the planet extremely hazardous for any future spacecraft, but the surface would remain protected. It is an interesting consideration for far future scenarios involving interstellar travel. Visiting Proxima d or any other planet with an extremely strong magnetic field would require spacecraft capable of navigating intense radiation environments. The radiation belts around such a world could rival or exceed those of Jupiter, which are among the most dangerous environments in our solar system for electronics and biological organisms. But that is a problem for a much later era of space exploration. For now, the pressing questions are more fundamental. Does Proxima d have an atmosphere? If so, what is it made of? Is Proxima b similarly protected? And how common are strong magnetic fields among the billions of rocky planets orbiting red dwarfs across the galaxy? These questions are within reach of current and near-future technology. The next decade of astronomical observations, with instruments like JWST, the extremely large telescopes, and the Square Kilometre Array, should provide significant answers. The Proxima Centauri system continues to surprise us. Each new observation peels back another layer of complexity, revealing a planetary system that is far more dynamic and interesting than its humble stellar host might suggest. A dim red dwarf, invisible to the naked eye, harboring planets with magnetic fields that rival gas giants. It is a reminder that the universe is reliably more interesting than our expectations. What makes this discovery particularly compelling is the sheer improbability of it, at least from the perspective of what we assumed before the data came in. Conventional wisdom held that small rocky planets orbiting close to red dwarfs would be geologically dead worlds, baked by radiation, stripped of their atmospheres, and magnetically inert. Proxima d defies every one of those assumptions. It is small but magnetically powerful. It is close to a flare-active star, but may have the very shield it needs to survive there. It sits outside the habitable zone but might have conditions at its poles that allow liquid water. It was supposed to be boring, and instead it might be one of the most geologically and magnetically active rocky worlds we know of. Science progresses when observations contradict expectations. That is how we learn, and the Proxima Centauri system has now given us one of the most productive contradictions in recent exoplanet science. If you have found this exploration of Proxima Centauri's magnetic planets fascinating, consider subscribing and sharing this with someone who loves space science. There are extraordinary discoveries being made right now about the worlds closest to us, and staying informed means being part of one of the most exciting eras in the history of astronomy. There is still an enormous amount we do not know. We do not know Proxima D's true mass, radius, or composition. We do not know if it has an atmosphere. We do not know the exact strength of its magnetic field to better than an order of magnitude. We do not know if Proxima b truly has a magnetic field, or if the suggestive evidence is caused by something else entirely. We do not know if there is a third rocky planet lurking in the system. But here is what we do know. Proxima d has a magnetic field. That field is strong, and it is causing measurable effects on its star. These are observed facts, not theoretical predictions. They provide a foundation on which future observations can build. The history of exoplanet science is still very young. The first exoplanet around a main sequence star was confirmed only in 1995. In the 3 decades since, we have gone from knowing of 0 exoplanets to confirming over 5,500. We have found planets made of diamond, planets that rain glass sideways, planets that orbit 2 suns, planets smaller than Mercury, planets larger than Jupiter, and now planets with magnetic fields stronger than anything in our solar system. Each discovery adds to a picture that grows more complex and more wondrous with every observation. The Proxima Centauri system, by virtue of its proximity, will remain at the forefront of this exploration for decades to come. It is the most accessible alien planetary system we have, and it continues to reward our attention with surprises. As of now, the scientific community is digesting these results and planning follow-up observations. Additional years of monitoring Proxima Centauri's flaring patterns will help refine the statistical confidence in the Proxima d magnetic field detection and potentially confirm or rule out a field around Proxima. Spectroscopic observations may reveal atmospheric signatures that would indicate whether the magnetic shield has actually succeeded in preserving an atmosphere. There are also theoretical questions that need addressing. How exactly does a planet as small as Proxima d generate such a strong field? What does this tell us about its internal composition? Is the core predominantly iron, and if so, What fraction of the planet does it occupy? How does tidal heating interact with the geodynamo to produce these results? These questions will drive both observational and computational research for years. The answers matter not just for Proxima d, but for our understanding of rocky planets everywhere. Every exoplanet we study teaches us something about the full range of possibilities for planetary formation and evolution. And sometimes, as with Proxima d, the lessons completely upend our prior assumptions. There is one more dimension to this discovery that deserves careful exploration, and it concerns the fundamental physics of how magnetic fields protect atmospheres over geological timescales. When we say that a magnetic field protects a planet's atmosphere, we are describing a process that plays out over billions of years. It is not a single event, but a continuous, ongoing interaction between the planet's magnetosphere, the stellar wind, and the upper atmosphere. The stellar wind is a constant outflow of charged particles from the star, primarily protons and electrons, moving at speeds of hundreds of kilometers per second. For a planet without a magnetic field, this wind directly impacts the upper atmosphere. The particles transfer energy to atmospheric molecules, heating them, and in some cases accelerating them to escape velocity. This is called sputtering, and it is one of the primary mechanisms of atmospheric loss. A magnetic field creates a standoff distance, called the magnetopause, where the dynamic pressure of the stellar wind balances the magnetic pressure of the planet's field. Beyond this distance, the stellar wind flows freely. Inside this distance, the planet's magnetic field dominates, and charged particles are deflected. The size of the magnetopause depends on the relative strengths of the stellar wind and the planetary field. A stronger planetary field pushes the magnetopause further out, providing a larger protective bubble. A stronger stellar wind pushes it closer to the planet, reducing protection. For Proxima d, with a magnetic field estimated at around 16 Gauss, the magnetopause would be located significantly further from the planet than Earth's magnetopause is from Earth. Even though Proxima Centauri's stellar wind is likely stronger than the solar wind at Earth's distance, because Proxima d orbits much closer, the planet's extremely powerful field should more than compensate. Calculations suggest that for a field of this strength, the magnetopause would be located at several planetary radii from the surface, providing a substantial buffer zone. Atmospheric molecules would need to climb far above the surface and travel well beyond the magnetopause before they could be entrained by the stellar wind and carried away. This dramatically reduces the rate of atmospheric escape. Over 4.8 billion years, the approximate age of the Proxima Centauri system based on stellar evolution models, a strong magnetic field could make the difference between retaining a significant atmosphere and losing it entirely. Without the field, models suggest that a planet like Proxima d could lose an Earth ocean equivalent of hydrogen in less than 1 billion years. With a field of 10 to 20 Gauss, that timescale extends to many billions of years, potentially longer than the current age of the system. This does not guarantee that Proxima d has an atmosphere today. It is possible that the planet formed without significant volatile content in the first place, or that early atmospheric loss before the magnetic field fully developed was catastrophic enough to strip away whatever atmosphere existed. But it means the magnetic field provides a viable pathway for atmospheric retention that was previously assumed to be blocked. The physics of atmospheric escape is actually far more complex than simple sputtering. There are multiple escape mechanisms, each with different dependencies on magnetic fields, atmospheric composition, and stellar radiation. Thermal escape, also called Jeans escape, occurs when molecules in the upper atmosphere have enough thermal energy to exceed the planet's escape velocity. This process depends on the temperature of the exosphere, the outermost layer of the atmosphere, and the molecular weight of the atmospheric gases. Light gases like hydrogen and helium escape more readily than heavier gases like nitrogen, oxygen and carbon dioxide. A magnetic field has minimal direct effect on thermal escape since the escaping molecules are mostly neutral. However, by reducing the heating of the upper atmosphere by stellar wind particles, the magnetic field indirectly reduces the rate of thermal escape as well. Non-thermal escape mechanisms include sputtering, ion pickup, and polar wind escape. Sputtering, as mentioned, involves direct momentum transfer from stellar wind particles to atmospheric molecules. Ion pickup occurs when neutral atmospheric molecules are ionized by stellar radiation, then picked up and accelerated by the stellar magnetic field. Polar wind escape happens when ions in the upper atmosphere are accelerated outward along open magnetic field lines near the poles. A planetary magnetic field strongly suppresses sputtering and ion pickup by keeping the stellar wind away from the atmosphere. However, it can actually enhance polar wind escape by providing magnetic field lines that channel ions away from the planet at the poles. This is one of the reasons why Mars researchers have debated whether a magnetic field would actually help Mars retain its atmosphere, since Mars's current atmospheric loss is dominated by non-thermal processes that a magnetic field might not fully prevent. For a planet like Proxima d, the situation is more favorable. The dominant atmospheric loss mechanisms at such close proximity to an active star are sputtering and ion pickup, both of which are strongly suppressed by a magnetic field. The enhancement of polar wind escape is a secondary effect that would remove far less atmosphere than the suppression of sputtering would save. The net result is that a strong magnetic field around Proxima d is overwhelmingly positive for atmospheric retention. It is not a perfect shield, as no shield is perfect, but it dramatically shifts the balance from atmospheric loss to atmospheric persistence. Another consideration is the evolution of Proxima Centauri's activity over time. Red dwarfs are most active when they are young. Their flaring frequency, XUV luminosity, and stellar wind strength all decrease as the star ages. Proxima Centauri, despite being roughly the same age as the Sun, is still quite active, but it was almost certainly more active in the past. During the first few 100 million years of the system's history, when Proxima Centauri was at its most active, the atmospheric erosion pressure on Proxima d would have been intense. This is the period when most atmospheric loss would have occurred, with or without a magnetic field. The key question is whether the magnetic field was already active during this early period. If Proxima d's magnetic field has been operating since shortly after the planet formed, which is plausible if tidal heating has been continuously active, then the planet would have had magnetic protection during the most dangerous phase of stellar activity. This could have preserved a significant fraction of its original atmosphere through the early bombardment and allowed it to persist into the present day. If the magnetic field developed later, after significant atmospheric loss had already occurred, then the protection would have come too late for the original atmosphere. However, subsequent volcanic outgassing could have rebuilt the atmosphere over time, and the magnetic field would have protected this secondary atmosphere from erosion. Either way, the presence of a strong magnetic field at the current epoch is encouraging. It means that whatever atmosphere exists now is being protected and will continue to be protected for the foreseeable future. Let us now consider the geological implications of Proxima d's magnetic field and tidal heating. A strong magnetic field implies a vigorously convecting liquid core. This in turn implies significant internal heat generation, likely dominated by tidal heating. But tidal heating does not only affect the core. It heats the entire interior of the planet, including the mantle. In our solar system, we see the dramatic effects of tidal heating on Jupiter's moon Io. Tidal forces from Jupiter flex Io's interior, generating so much heat that the moon is covered in active volcanoes. Io erupts continuously, resurfacing itself so rapidly that it has virtually no impact craters. The surface is young, geologically speaking, because it is constantly being buried by fresh volcanic material. Proxima D's tidal heating may not be as extreme as Io's, since the tidal forces from a star at 5-day orbital distance are different from those of a gas giant on a close moon, but the heating could still be substantial. This could manifest as widespread volcanic activity, releasing gases that build and maintain an atmosphere. Volcanic outgassing on Earth has been a major source of atmospheric gases throughout our planet's history. Carbon dioxide, water vapor, sulfur dioxide, and nitrogen are all emitted by volcanoes. On Proxima D, similar processes could be operating, potentially producing a thick volcanic atmosphere dominated by carbon dioxide and sulfur compounds. If the volcanic activity is intense enough, Proxima D could be something like a Super Io crossed with Venus, a world with relentless eruptions, a dense acidic atmosphere, and extreme surface conditions. Alternatively, if the tidal heating is more moderate, the planet might have intermittent volcanic activity similar to early Earth, with a thinner atmosphere and more temperate surface conditions in some regions. The presence of a magnetic field also has implications for the planet's crustal structure. On Earth, the magnetic field interacts with the crust to create patterns of magnetic anomalies, stripes of alternating magnetic polarity that record the history of geomagnetic reversals in the oceanic crust as it forms at mid-ocean ridges and spreads away. These patterns were instrumental in confirming the theory of plate tectonics in the 1960s. If Proxima D has plate tectonics, its strong magnetic field would create similar anomaly patterns in its crust. Of course, we have no way of detecting such patterns on an exoplanet with current technology, but the theoretical possibility that plate tectonics and a strong magnetic field could coexist on this world is intriguing from a habitability perspective. Plate tectonics is often cited as an important factor for long-term habitability. It recycles carbon between the atmosphere and the interior through the carbonate silicate cycle, acting as a thermostat that regulates surface temperatures over geological timescales. It also promotes volcanic activity, which releases greenhouse gases and creates diverse surface environments, from ocean trenches to mountain ranges, that could support a wide variety of life forms. Whether Proxima D has plate tectonics is entirely unknown. The planet may be too small for plate tectonics, as the lithosphere of a small planet may be too thick relative to the mantle for plates to form and move. Or the tidal heating could thin the lithosphere enough to enable plate-like behavior. Or the planet could have a completely different tectonic regime, such as a stagnant lid like Mars or an episodic overturn like some models suggest for Venus. The point is that Proxima D's strong magnetic field and implied tidal heating make it a far more geologically interesting object than a cold, dead rock. It is likely a geologically active world with ongoing processes that shape its surface and atmosphere. Let us now return to the broader question of how common magnetic fields are on rocky exoplanets and what this means for the search for life. Before the discoveries around Proxima D and YZ Ceti b, there were theoretical reasons to expect that magnetic fields on close and rocky planets around red dwarfs could go either way. Arguments against strong fields included the slow rotation of tidally locked planets, which could weaken the dynamo, and the small sizes of many of these planets, which would cause them to cool and solidify their cores quickly. Arguments in favor of strong fields included tidal heating, which could maintain liquid cores, and the possibility of large iron cores, which would provide more conducting fluid. There were also some theoretical models suggesting that even slowly rotating planets could generate magnetic fields through alternative dynamo mechanisms, such as precession-driven or tidally driven dynamos. The observations now appear to favor the optimistic view. Both Proxima D and YZ Ceti b have magnetic fields far stronger than most theoretical predictions anticipated. This suggests that either the tidal heating effect is more powerful than modeled, or there are additional dynamo mechanisms at play that the theories have not fully captured, or both. If future observations confirm magnetic fields on additional rocky exoplanets around red dwarfs, it could establish strong magnetic fields as a common feature of these worlds, rather than a rare exception. This would have enormous implications for the Drake equation, the famous formula that estimates the number of communicating civilizations in the galaxy. One of the key terms in the Drake equation is the fraction of planets with conditions suitable for life. If most rocky planets around red dwarfs lack magnetic fields and therefore cannot retain atmospheres, this fraction would be relatively small. But if strong magnetic fields are common, dramatically more planets could maintain atmospheres and potentially support life. The number of potentially habitable worlds in the galaxy could increase by orders of magnitude. The discovery also has implications for how we prioritize targets in the search for biosignatures. If we know that a planet has a magnetic field, it moves up the priority list because we know it has a better chance of retaining an atmosphere. Future missions designed to characterize exoplanet atmospheres, such as the proposed Habitable Worlds Observatory, could incorporate magnetic field detection as a screening criterion for selecting the most promising targets. This brings us to the question of how we will detect magnetic fields on exoplanets more broadly. The star-planet interaction method used for Proxima D and YZ Ceti B has proven effective, but it requires very specific conditions. The planet must orbit close enough to the star for its magnetic field to detectably influence stellar activity. The star must be magnetically active, which red dwarfs generally are. And we need long-term, high-cadence monitoring of the star's activity to identify periodic correlations with planetary orbits. These requirements limit the method to close-in planets around active stars. For planets in wider orbits or around less active stars, the method may not work. Alternative detection methods will be needed to survey the full population of rocky exoplanets. Radio emission detection remains a promising but so far unproven method. The square kilometer array may change that when it comes online. If rocky exoplanets emit radio waves analogous to Jupiter's decametric radiation, the SKA's sensitivity should be sufficient to detect them from nearby systems. Another proposed method involves detecting the signatures of auroral emission in the atmospheres of transiting exoplanets. On Earth, the interaction of solar wind particles with the magnetosphere produces auroras, which emit light at specific wavelengths. If a similar process occurs on an exoplanet, it might be detectable during transit observations as an excess signal at those wavelengths. This method would require extremely precise spectroscopy, but it is within the theoretical capabilities of next-generation instruments. There is also the possibility of detecting magnetic field effects through the polarization of light. A magnetic field can polarize light that passes through or reflects off a planet's atmosphere. By measuring the polarization of light from an exoplanetary system at different orbital phases, it might be possible to infer the presence of a magnetic field. This technique is still in the theoretical stage, but it could potentially be applied to directly imaged exoplanets in the future. Each of these methods has different strengths and limitations, and together they could provide a comprehensive picture of magnetic fields on rocky exoplanets. We are still in the early days of this field, and the Proxima D and YZ Ceti B detections are the trailblazers. Let us now consider what the Proxima Centauri system tells us about planetary system architecture around red dwarfs more generally. The system has at least 2 and possibly 3 or more rocky planets in close orbits. Proxima D at 5 days, Proxima B at 11.2 days, and potentially another planet between them or interior to Proxima D. This is a compact system with multiple rocky worlds packed into a small orbital space. This architecture is actually quite common around red dwarfs. The TRAPPIST-1 system, discovered in 2017, has 7 rocky planets all orbiting within the distance equivalent to Mercury's orbit around our Sun. The innermost planet completes an orbit in just 1.5 days, while the outermost takes about 18.8 days. Several of the TRAPPIST-1 planets are in or near the habitable zone. The Kepler Space Telescope found that compact multi-planet systems are the norm around low-mass stars. Red dwarfs commonly host multiple small planets in tight orbits, often in or near mean motion resonances, where the orbital periods are related by simple ratios. This architecture may be a natural outcome of the planet formation process around small stars, where the protoplanetary disk is smaller and the planets form closer together. If strong magnetic fields are common on close and rocky planets around red dwarfs, then these compact multi-planet systems are full of magnetically shielded worlds. The TRAPPIST-1 system, for example, has 7 rocky planets that could potentially all have magnetic fields enhanced by tidal heating and gravitational interactions between the planets. The TRAPPIST-1 planets are particularly interesting in this context because they are in orbital resonances that maintain their eccentricities and thus their tidal heating. This is directly analogous to the Galilean moons of Jupiter, where orbital resonances maintain tidal heating in Io, Europa, and Ganymede. If tidal heating drives magnetic dynamos, then resonant multi-planet systems around red dwarfs could be magnetic field factories. We do not yet have evidence for magnetic fields on the TRAPPIST-1 planets. The star is much further away than Proxima Centauri, roughly 40 light-years versus 4.2, which makes star-planet interaction signals harder to detect. But the physical conditions are similar, and if the Proxima d results are representative, there is good reason to expect magnetic fields in the TRAPPIST-1 system as well. This is one of the most exciting aspects of the discovery. It is not just about one planet around one star. It suggests a general mechanism that could operate on billions of planets across the galaxy, fundamentally changing our assessment of how common habitable environments are. Let us spend some time discussing the stellar magnetic field of Proxima Centauri itself, because understanding the star is crucial to understanding the interaction with its planets. Red dwarfs like Proxima Centauri are fully convective. Unlike the Sun, which has a radiative core that transports energy through photon diffusion, and a convective outer zone that transports energy through bulk fluid motion, red dwarfs below about a third of a solar mass transport energy convectively all the way from the core to the surface. This has profound implications for their magnetic behavior. The Sun's magnetic field is thought to be generated primarily at the tachocline, the boundary between the radiative core and the convective envelope. The shearing motion at this interface stretches and amplifies magnetic field lines through a process called the alpha-omega dynamo. Red dwarfs do not have a tachocline, so their dynamo must operate through a different mechanism. Despite this theoretical puzzle, red dwarfs generate extremely strong magnetic fields. Proxima Centauri's surface field is estimated at several hundred to over 1,000 Gauss, compared to the Sun's average surface field of about 1 to 2 Gauss. The magnetic topology is also different. While the Sun's field is complex and multipolar, many red dwarfs have predominantly dipolar fields, meaning the field is organized into a simple north-south configuration. A strong, dipolar stellar field has important implications for star-planet interactions. A dipolar field is more organized and has a more predictable influence at planetary orbital distances than a complex multipolar field. This makes it easier for a planetary magnetic field to have a coherent interaction with the stellar field, which is why the star-planet interaction signal is detectable. The strength of Proxima Centauri's magnetic field also means that its magnetosphere extends far out into the system. The stellar magnetic pressure creates a zone of influence that likely encompasses the orbits of both Proxima d and Proxima. Within this zone, a planet's own magnetic field must push back against the stellar field to maintain its magnetosphere. The fact that Proxima d is able to do this, and to do it so powerfully that it triggers flares, speaks to the exceptional strength of the planet's field. It also means that the magnetic environment around Proxima d is extraordinarily dynamic. The planet is immersed in a stellar magnetic field hundreds of times stronger than the solar wind's magnetic field at Earth's distance. The interaction between the planetary and stellar fields must generate intense electromagnetic phenomena, potentially including radio emissions, auroral activity on both the planet and the star, and magnetic reconnection events that release bursts of energy. Proxima d may be one of the most electromagnetically active environments in the stellar neighborhood. A planet and star locked in a constant magnetic tug of war, with flares, auroras, and electromagnetic storms as the visible manifestations of their interaction. This environment would be hostile in many ways, but also scientifically fascinating. If we could observe it up close, we would be seeing magnetic physics operating on a scale that has no analog in our solar system. The closest parallel might be the Io-Jupiter interaction, but even that is a pale shadow of what happens when a strongly magnetized rocky planet orbits within the corona of a magnetically active red dwarf. Let us also address the question of how the magnetic field discovery affects the ongoing debate about whether red dwarf planets can be truly habitable. The habitability debate for red dwarf planets has raged for decades. Proponents point to the extreme longevity of red dwarfs, the abundance of rocky planets in their habitable zones, and the theoretical possibility of atmospheric heat redistribution on tidally locked worlds. Skeptics counter with the intense stellar activity, the risk of atmospheric stripping, the potential for tidal locking to create extreme temperature gradients, and the possibility that synchronous rotation and close proximity to the star could suppress geological activity. The magnetic field discovery addresses one of the strongest skeptical arguments directly. The atmospheric stripping concern was based on the assumption that red dwarf planets would lack the magnetic protection needed to survive their stars' flares. If strong magnetic fields are common on these worlds, this argument loses much of its force. The tidal locking concern is also partly addressed. While tidal locking does slow a planet's rotation, the Proxima d results show that synchronous rotation is still compatible with a powerful magnetic dynamo. A 5-day rotation period is slow compared to Earth's 24 hours, but it is apparently sufficient to organize a dynamo capable of generating a field 20 or more times stronger than Earth's. The temperature gradient concern requires a different solution, specifically an atmosphere thick enough to transport heat from the day side to the night side. And this is exactly what a magnetic field makes possible by preventing atmospheric erosion. In other words, the magnetic field discovery creates a positive feedback loop for habitability. The magnetic field preserves the atmosphere. The atmosphere redistributes heat. The heat redistribution moderates temperatures, and moderate temperatures, combined with the presence of an atmosphere, create conditions where liquid water and potentially life could exist. This does not mean that Proxima d is habitable. It is too close to its star for conventional habitability, though polar regions might be temperate. But for Proxima b, which sits squarely in the habitable zone, the case for potential habitability has strengthened considerably. The next major milestone will be detecting an atmosphere on one of the Proxima Centauri planets. If JWST, or a ground-based extremely large telescope, can confirm the presence of atmospheric gases on Proxima b, or even Proxima d, it would validate the hypothesis that magnetic fields enable atmospheric retention around red dwarf planets. This would be one of the most significant discoveries in the history of exoplanet science. And if the atmosphere contains biosignature gases, well, that would change everything. We are not there yet. We are still at the stage of establishing the basic physical conditions on these worlds. But the magnetic field discovery has opened a door that many thought was closed. Behind that door lies a universe of magnetically shielded rocky worlds orbiting the most common stars in the galaxy, each one a potential home for conditions very different from but possibly as alive as those on Earth. The nearest star has more secrets than we imagined, and we are only just beginning to learn them. One of the most remarkable aspects of this entire story is how much we have learned about Proxima d despite knowing so little about its basic properties. We do not know its radius. We do not know its exact mass. We cannot image its surface or directly sample its atmosphere. Yet we know it has a magnetic field, we know that field is strong, and we know it interacts with its star. This speaks to the power of indirect detection methods in astronomy. Throughout the history of the field, some of the most important discoveries have been made not by looking at objects directly, but by observing their effects on other things. Neptune was discovered because its gravity perturbed the orbit of Uranus. Dark matter was inferred because galaxies rotate faster than their visible mass can explain. The cosmic microwave background was detected as a faint hiss of radio noise that was actually the remnant radiation from the birth of the universe. Proxima D's magnetic field was detected because it perturbs its star. The planet is too small and too far away to reveal its magnetic field directly. But its influence on Proxima Centauri's magnetic behavior is measurable. This is science at its most elegant, finding the hidden by watching the visible. As we stand at this moment in the history of exoplanet science, there are still far more questions than answers about the Proxima Centauri system. What is Proxima d actually like? Does it have volcanoes, oceans, polar ice caps, a sky? We do not know. Does Proxima b have a magnetic field comparable to its inner sibling? Probably, but we cannot say for certain. Is there a third rocky planet in the system, a tiny world hiding in the gravitational shadows of the other two? Maybe. What we can say with confidence is that the Proxima Centauri system is more complex, more active, and more scientifically rich than anyone expected. And the discovery that its innermost known planet has a magnetic field rivaling Jupiter's is a finding that will influence exoplanet research for years to come. The science continues, the observations accumulate, and with each new piece of data, the picture becomes a little clearer and often a lot more surprising. The nearest stars have not finished surprising us yet, not by a long shot. Now let us delve into one of the most subtle but important aspects of this entire discussion, the relationship between planetary magnetic fields and the chemistry of atmospheres under intense stellar radiation. When high-energy photons from Proxima Centauri strike the upper atmosphere of a planet, they drive a cascade of chemical reactions. Ultraviolet photons can break apart molecules through a process called photodissociation. Water molecules, for instance, can be split into hydrogen and oxygen atoms. Carbon dioxide can be broken into carbon monoxide and oxygen. Nitrogen molecules can be split into individual nitrogen atoms that then react with other species. On Earth, this photochemistry is a central feature of our upper atmosphere. The ozone layer, which protects the surface from harmful ultraviolet radiation, is itself a product of photochemistry. Ultraviolet light splits oxygen molecules into individual oxygen atoms, which then combine with other oxygen molecules to form ozone. The ozone, in turn, absorbs ultraviolet radiation, creating a protective shield. For a planet around a red dwarf, the photochemistry would be different because the spectrum of incoming radiation is different. Red dwarfs emit relatively less visible and ultraviolet light than the sun, but proportionally more far ultraviolet and X-ray radiation during flares. This altered spectrum would drive different chemical reactions in the atmosphere. Some models suggest that the atmospheres of red dwarf planets could develop unusual chemical compositions as a result. For example, the ratio of ozone to other oxygen species might be very different from Earth. The abundance of certain molecules like nitrous oxide or methane could be significantly altered. Water vapor in the upper atmosphere might be more efficiently destroyed, leading to hydrogen loss even in the presence of a magnetic field. Understanding this atmospheric chemistry is crucial for interpreting future observations. When we eventually point powerful telescopes at Proxima b or d and measure their atmospheric spectra, the chemical fingerprints we find may look nothing like Earth's. That does not mean the atmosphere is lifeless. It means the atmospheric chemistry has been shaped by a very different stellar environment. A magnetic field plays a role in this chemistry indirectly. By preventing atmospheric stripping, the magnetic field ensures that there is an atmosphere present for photochemistry to act upon. Without the field, the atmosphere would erode away, and there would be no chemistry to speak of. With the field, the atmosphere persists but is continuously processed by stellar radiation, creating a dynamic chemical environment that evolves over time. This dynamic processing could actually be beneficial for prebiotic chemistry. On early Earth, the energy from ultraviolet radiation is thought to have driven the chemical reactions that assembled the first complex organic molecules, the precursors to life. If a similar process operates on planets around red dwarfs, the intense radiation environment, combined with a magnetically preserved atmosphere, could create conditions favorable for the emergence of life. This is speculative, of course. We do not know whether the specific conditions on Proxima d or b are conducive to prebiotic chemistry, but the magnetic field discovery removes one of the major barriers to habitability and opens the door to a much wider range of possible atmospheric and chemical environments. Let us also consider what the discovery means in the context of the Fermi paradox, the apparent contradiction between the high probability of extraterrestrial civilizations and the lack of evidence for them. One potential resolution to the Fermi paradox is the rare Earth hypothesis, which suggests that while simple life may be common, the conditions required for complex life and intelligence are extremely rare. The habitability of red dwarf planets has been a key point of contention in this debate. If red dwarf planets are generally uninhabitable, then the vast majority of the galaxy's real estate is off-limits for life, making complex life rarer and potentially explaining the silence. But if magnetic fields enable atmospheric retention on red dwarf planets, and if such magnetic fields are common, then the habitable real estate in the galaxy expands enormously. This makes the rare Earth hypothesis harder to sustain and deepens the mystery of the Fermi paradox. Of course, the Fermi paradox involves many more factors than just the number of habitable planets. The probability of life originating on a habitable planet, the likelihood of complex life evolving, the chances of intelligence developing, and the longevity of technological civilizations all play roles. But the number of candidate worlds is a foundational variable, and the magnetic field discovery suggests it could be much larger than previously estimated. This does not solve the Fermi paradox, but it reframes it. If there are potentially billions of magnetically shielded, atmosphere-bearing rocky worlds around red dwarfs in the Milky Way alone, then the question of why we have not detected signs of extraterrestrial intelligence becomes even more pressing. Let us now turn to a practical consideration that bridges current research and future technology. How would we confirm Proxima D's magnetic field with higher confidence, and what would that require? The current detection is based on a statistical correlation between the planet's orbit and the star's flaring activity, with a confidence level of approximately 99.9%. While this is strong evidence, the gold standard for a detection in physics is 5 sigma, corresponding to a probability of less than 1 in 3.5 million that the result is due to chance. To reach 5 sigma, the researchers would need either a longer observational baseline, more precise measurements of flare timing and intensity, or independent confirmation from a different detection method. A longer baseline is the most straightforward approach. The current study used 3 years of data. Extending the monitoring to 5 or 10 years would provide more orbital cycles of Proxima d and allow for more robust statistical analysis. The challenge is that telescope time is competitive and expensive, and maintaining consistent observations over many years requires sustained institutional commitment. More precise measurements could come from space-based telescopes that observe in X-ray or extreme ultraviolet wavelengths, where flare signatures are strongest. Current X-ray observatories like Chandra and XMM Newton have the sensitivity to observe Proxima Centauri's flares, but they do not provide continuous coverage. A dedicated monitoring campaign with one of these telescopes could significantly improve the precision of the flare-orbit correlation. Independent confirmation could come from radio observations. If Proxima D's magnetic field generates detectable radio emissions, either from the planet itself or from the star-planet interaction, this would provide a completely independent line of evidence. The LOFAR radio telescope in the Netherlands and the upcoming Square Kilometre Array are both capable of searching for such signals. Another possibility is detecting the magnetic field's effect on Proxima D's atmosphere, if it has one. A magnetic field shapes the way an atmosphere interacts with the stellar wind, creating an asymmetric structure with a compressed day side and an extended magnetic tail on the night side. If Proxima D transits its star, which we do not currently know, this asymmetric structure might be detectable in transit observations as a characteristic spectral signature. Even if Proxima D does not transit, it might be possible to detect atmospheric asymmetries through high-resolution spectroscopy of the star during different phases of the planet's orbit. This is technically challenging, but not impossible with next-generation instruments. The path to confirmation is clear, even if the journey will take years, and each step along that path will teach us more about this remarkable little world and the forces that shape it. Let us consider one final perspective on this discovery. When we look at the history of scientific understanding of planetary magnetic fields, a clear pattern emerges. At each stage, we have been surprised by what we found. When spacecraft first measured Mercury's magnetic field in the 1970s, scientists were surprised that such a small, slowly rotating planet had a field at all. When Voyager 2 measured the magnetic fields of Uranus and Neptune in the 1980s, the bizarre tilts and offsets of these fields confounded existing theories. When Ganymede's magnetic field was confirmed in the 1990s, it was unexpected for a moon to have its own intrinsic field. Now with Proxima D, we are surprised again. A planet a third the mass of Earth generating a field comparable to Jupiter's. Every time we have looked at a new category of object, the magnetic fields have been different from what we expected. Stronger, weaker, tilted, offset, or generated by mechanisms we did not predict. This pattern should make us humble about our theoretical predictions and enthusiastic about the observations yet to come. The universe has consistently shown that magnetic fields are more diverse, more powerful, and more prevalent than our models suggest. If this trend continues, the ongoing surveys of exoplanetary magnetic fields will likely reveal a landscape even more varied and surprising than what we currently imagine. The magnetic planets of Proxima Centauri represent a beginning, not an end. They are the first clear look at a phenomenon that may be ubiquitous across the galaxy. And as our instruments improve and our surveys expand, the full picture will gradually come into focus. It is a picture that may include billions of magnetically shielded worlds, each with its own unique geological and atmospheric character, each a potential laboratory for the experiment of life. The nearest star has planets with magnetic fields. That single finding opens a window onto a galaxy that may be far more hospitable than we dared to hope, and the view through that window is just beginning to sharpen. What remains to be discovered about the Proxima Centauri system alone could fill years of research and hundreds of papers. What remains to be discovered about magnetic fields on exoplanets across the Milky Way could transform our understanding of where life can and does exist. We are at the very beginning of this story, and the beginning has already been extraordinary. There is a thread running through all of this that is worth pulling on a bit further. It is the idea that proximity to a red dwarf, long considered a curse for planetary habitability, may actually function as something closer to a blessing in disguise. This idea has been hinted at throughout our discussion, but it deserves to be stated plainly because of how counterintuitive it is. For decades, the standard narrative went something like this. Red dwarfs are hostile to life. Their habitable zones are so close to the star that any planet residing there would be tidally locked, pummeled by flares, and stripped of its atmosphere. The only real hope for life in the galaxy was around sun-like stars, where the habitable zone sits at a comfortable distance and conditions are more benign. This narrative was not baseless. It was grounded in real physics, but it was also based on incomplete information. We did not know whether planets in tight orbits around red dwarfs could generate strong magnetic fields. We assumed they could not, or at least that such fields would be too weak to matter. The Proxima D discovery challenges that assumption head-on. The emerging picture is more nuanced. Yes, red dwarfs bombard their close-in planets with flares and stellar wind. But those same tight orbits generate tidal forces that heat the planet's interior, maintain a liquid core, and drive a magnetic dynamo. The dynamo produces a magnetic field that shields the atmosphere from the very stellar wind, and flares that the tight orbit exposes it to. The danger and the defense arise from the same physical circumstance. This is a beautiful example of physical feedback in nature. The system is not simply dangerous or simply safe. It is both, simultaneously, with the protective mechanism arising organically from the same conditions that create the threat. There is no external intervention required, no lucky accident, just the straightforward operation of physics at the right scale and distance. If this feedback mechanism is general, meaning it operates on most rocky planets in the habitable zones of most red dwarfs, then the implications are staggering. It would mean that the most common type of star in the galaxy naturally produces the conditions for both the threat and the defense of planetary atmospheres. It would mean that the Milky Way is filled with magnetically armored rocky worlds, each one independently solving the atmospheric retention problem through the same physical mechanism. We cannot confirm this yet. Two detections do not prove universality, but the physical reasoning is sound, and the observations so far are consistent with it. If the next several magnetic field detections on rocky exoplanets around red dwarfs also show strong fields, the case for universality will strengthen rapidly. There is another angle worth exploring here, and it relates to how we might use magnetic field information to prioritize targets for atmospheric characterization with future telescopes. The proposed Habitable Worlds Observatory, a NASA flagship mission concept, would be designed specifically to directly image Earth-like planets around nearby stars and characterize their atmospheres through spectroscopy. The mission would need to select a relatively small number of targets from a large pool of candidates, and the selection criteria would determine the mission's chances of success. Currently, the main criteria for target selection include the planet's size, its location relative to the habitable zone, and the brightness and distance of its host star. But magnetic field information could add a powerful additional criterion. A planet known to have a strong magnetic field would be a more promising target because it is more likely to have retained an atmosphere. Investing precious telescope time on a planet with a confirmed magnetic shield could dramatically improve the odds of detecting atmospheric gases and potentially biosignatures. This practical consideration underscores why the Proxima D discovery is not just scientifically interesting, but also strategically important for the future of exoplanet exploration. It provides a new dimension of information that can make our search for life more efficient and more targeted. The same logic applies to the search for technosignatures, artificial signs of technology produced by extraterrestrial civilizations. If a planet has a magnetic field and an atmosphere, it is a more plausible candidate for hosting a technological civilization that might produce detectable signals. Radio SETI searches, for example, could prioritize planets with known magnetic fields on the reasoning that such planets are more likely to harbor the conditions necessary for complex life and technology. This is getting ahead of ourselves, of course. We have not yet confirmed an atmosphere on Proxima D or B, let alone detected biosignatures or technosignatures. But the magnetic field discovery opens the door to a series of follow-up investigations that could, step by step, bring us closer to answering the ultimate question of whether life exists beyond Earth. Let us take a step back and consider the scale of what we are discussing. When we talk about the habitability of red dwarf planets, we are talking about the potential for life on a galactic scale. Red dwarfs are everywhere. They outnumber all other types of stars combined. They are found in the spiral arms of the Milky Way, in its central bulge, in its halo, in globular clusters, and in satellite galaxies orbiting the Milky Way. If even a small percentage of the rocky planets orbiting these stars have magnetic fields strong enough to retain atmospheres, the total number of atmosphere-bearing rocky worlds in the galaxy could number in the tens of billions. Some of these would be in the habitable zone. Some would have water. Some would have conditions conducive to the origin of life. And some, perhaps, would actually have life. The numbers are speculative, but the logic is grounded in observed physics. Strong magnetic fields have been detected on 2 rocky planets around red dwarfs. The mechanism for generating those fields, tidal heating from close stellar proximity, should operate on most rocky planets in similar orbits. And the protective effect of those fields against atmospheric stripping is well established from solar system physics. Each link in this chain of reasoning is supported by evidence. The chain as a whole points to a galaxy that is far more biologically promising than the pessimistic assessments of just a few years ago suggested. There is something profoundly encouraging about that. For decades, the question of extraterrestrial life has been plagued by uncertainties, each one potentially reducing the number of habitable worlds to a discouragingly small number. The magnetic field discovery pushes back against one of the most significant of those uncertainties. It does not prove that life is common, but it removes one of the strongest arguments against it. And in a field where progress is measured in incremental expansions of what is possible, removing a major barrier counts as a significant advance. Let us close by considering what comes next for the Proxima Centauri system, and for the study of exoplanetary magnetic fields more broadly. In the near term, continued monitoring of Proxima Centauri will refine the magnetic field measurements for Proxima D and potentially confirm a field around Proxima. This work can be done with existing ground-based telescopes and does not require new technology, only sustained observat.